Okay.
This is Francis on
Oh, Francis. Okay. I didn't realize he's doing that too. It's a good model. Okay. We haven't covered everything from lecture 2 in the course, so we're going to go over those first. So I've updated a couple things here. So first of all, this will be the last lecture on Thursday, and we're going to be moving over to week 3, which will be next Tuesday. So I think I'll do this just because there's too little time between Thursday and Tuesday. So I'll try to narrate the lecture again. But then from the 4th all the way to the 13th, we'll have people in the class do the presentation and the questioning. Hopefully we'll have enough people so we don't have problems with having duplicate people present twice, because that wouldn't be fair. Okay, so in that case, probably what I'll do is I'll ask some of my staff to narrate the things. Okay, so last time we actually didn't finish going over all of the image classification lecture, this part. We finished K-nearest neighbor, but we hadn't gotten to the linear classification, so we're going to continue on with that. Okay, so I just download this, and then we'll talk from there. Okay, I think I need to go to a single page. Okay, so last time we talked about K-nearest neighbors. We said that for image classification, we can understand a very simple algorithm for K-nearest neighbors, which is that you start with a training set, right? You start with a training set, and you must predict labels on the test set. And you can basically, for K-nearest neighbors, just have an idea of a distance function. Function is, then you can classify images with respect to each other. So we saw a couple instances of that, here was the L1 distance defined, where we would have a pixel and another pixel on a training image, and we were trying to compute this distance value. This distance value just tells us the distance between a test image and a training image, or any pair of images, and compute it as a pixel difference per pixel. So 56 minus 10 would equals 46. 32 minus 20 would get us 12. You take all of these numbers, sum them together, and that represents some type of distance value, right, between one picture and another. And it's hopefully obvious to us if we give the same image, let's say we duplicate the training image and use it as the test image, then the absolute value difference would be 0 for all of the pixels, and we get a distance of 0, which is exactly what we want, right? So with this type of distance value, we can compute for any test image how far it is, or what's the distance value between a test image and a training image. And that led us to the nearest neighbor algorithm, which basically says we don't do anything to the training data, we just memorize it, right? But when we do the prediction, we have to loop over every single image in the training data, right? This is what this part does here, right? I go through all of the images in my data set, and I subtract the distances, sum them together for every pixel, and I get a distance for that particular image and the test image. And then out of all of the images in the training set, I pick out the one that has the minimum value, and I say that's the prediction, right? And so what you end up is something like this. So let's say you have this image of a frog here, and we try to pick the image in our training data set that has the least difference between this on a pixel by pixel basis, and I would pick a cat. So this one is obviously wrong here because a frog is not a cat. We would just, in this algorithm, just call the frog a cat because that's the closest one. Of course, there are cases that are correct, like this Maltese dog looks like this Maltese dog. At least that's the one that's closest, so it gets transferred over correctly. Okay, and there are many different ways to calculate this distance matrix. We'll come back to these ideas later. The one that we just looked at was Manhattan distance. So taking each dimension separately, thinking of each of those contributing independently of each other, and then summing up the value. And Euclidean distance makes a function of all of the values are being correlated, and you get a much more interpretation that is a bit more Cartesian in our sense of a Euclidean distance. Okay, so we're not going to talk exactly that much about this part, so we'll just go on from here. And basically, we said that with a K-nearest neighbor algorithm, we would select the image that's closest, or we, in the case where there is noise, maybe we would want to take a vote of the nearest neighbors with a number of neighbors, not just one, but several. So we might pick 3 or 5. Odd number is usually good so that we can break ties easily. And that came to some of the pictures we saw here. So for example, here, you have k equals 3, right? So that means for this dot here, even though this dot is yellow, we are going to consider this noise because you know, if we pick 3 neighbors around any particular point around that yellow dot, the yellow dot will only be one of the 3 neighbors. The other 2 are going to be green. So we're going to go with the majority classification. So there was a quick question, and I think many people understand that. What are all these white regions here? What do they represent?
The areas where there's not enough information to label it either any of the colors.
Okay. So that's right. So here, if we pick this point where the cursor is, we pick the 3 closest point, we get the green one that's within the radius of this spotlight. But we'd probably get 1 purple and 1 blue one too. So there's no clear majority here. So that's why this is colored white. But you can break ties arbitrarily. You can say, okay, I take the closest point. In this case, it would be green. Or, you know, you could take some other weighted value of that, right? Okay, so that's what those white regions represent. And you can try the demo out. They've nicely put up the demo on this website here, which we played around last time. Okay, so all of these are hyperparameters. What's the best distance value to use, L1 or L2, or, you know, another type of distance value. Usually what we find is that when we have a distance value, it helps to know something about the data set and what's useful for it. And then for k, again, you could use any value of k. What's the right one to use? We don't know. So typically what we do is we try to learn the hyperparameters by training multiple learning algorithms and then making choices on that. All right. So I think we went over hyperparameter settings, so I'm not going to go through this part. And we talked about the cursive dimensionality. So we're going to talk about the next part, which is linear classification. That's the new topic for today. So linear classifiers are a really, really important building block. And really, they've been around for a very, very long time, since the 1970s, 1960s. And in many ways, what we're doing with deep learning today is just doing things that people had been doing since the 1970s. But because we have the computational firepower to do it, now it's starting to work. So it's not particularly new technology. It's just that we're going to use them as atoms or layers, if you will. And you can think of it as this picture of a building block. So you just build larger structures out of very simple classifiers. And with those linear classifiers, although each of them individually can only draw hyperplanes, together they can warp the space arbitrarily complex to represent something more complex. So the idea is that each layer in this classifier, let's say our data is down here, we have some linear units that are going to learn some plane, but those are going to then feed into another level of units that are going to also do linear classification, but over the output of this layer. And then they're going to be able to bend space in some other way. And the idea originally was, as I told you in the first lecture, that our vision system is really organized hierarchically, right? We see visual primitives as being edges and you know, contrasts. And from that, we build up a representation of textures. We build up a representation of movement. And then from that, we start to recognize patterns and then objects. And from that, so all of those represent different layers going up the spectrum, right? And that was the idea that we got from biology, but we can also take that inspiration and work it into an artificial neural network, or ANN. or now it's more popularly called deep learning, right? But that's basically all it is. It's a bunch of linear classifiers. Okay, so here you can see the types of problems that we're trying to generate. This is the semantic understanding that we wish. So last week we showed a picture of Obama stepping on a scale, and this is the holy grail of computer vision, is to be able to tell us things like this, right? So this type of information right now is possible to do because we're thinking about object detection. Right, so we can recognize images of, let's say, babies or girls or Lego sets, etc. But we don't know the story behind that. We don't know the sentiment or the context behind it. So we're getting to this level where we can do this type of work, and this was actually published work by the authors at Stanford to generate image descriptions from images themselves, looking at a very large set of images and their descriptions. So you can think of the training data as a vector X, which has its image as one part of the vector and the description as another part of the vector, feeding that through some type of system, and then learning how to construct new descriptions from those images. Okay, so in fact, it's not that complicated. We can use the same type of technology that we use for vision for natural language processing and treat the image as a plane, right? Where we're going to use this system that we developed last time, which is just taking a picture, stringing it out into a long vector, and then feeding that into a neural network. But also for natural language, doing the same thing here. And natural language is actually very much well represented by a serial representation, right? So you have one word coming after the other. Okay, so we can project it in that way. It's a serial, time series type of input. And we just have to tune our learning algorithm to represent time series input. And there's another algorithm for that you might learn later on called an LSTM, or long short-term memory system, and similar things like that, like a recurrent or recursive neural network that allows us to encode entire vectors of spatial and temporal information. Okay. So let's take a look at how linear classifiers work. So let's say we have this data set, CFAR 10. It's called 10 because there's 10 classes of output. So you can see all the 10 things that they put on this on the left-hand side. And this is actually a subset of the whole image data set. So basically you have 50,000 images and 10,000 test images. And each of those are 32 by 32 pixels with RGB information. That's why there's a free at the end. So there's a separate number for red, green, and blue. And what we're going to do is we're going to stretch this array of integers all out into a single vector, right? So you multiply 32 times 32 times 3. That's the total number of numbers that are in an image, okay? So 3072. And we're going to call this X, right? This thing over here. And what we're going to learn is a model, okay? That's why we have this W here, a model of weights. Okay, and instead of doing what we did in KNN, which is just to define a distance metric, here what we're trying to say is this W represents a compact representation of the output of the learning algorithm. Okay, so all we're going to get out of training everything is 3072 numbers. Okay, and this number represents what the model has learned. So this is why we called it a parametric approach. Right, that we're encapsulating all of the knowledge the algorithm has created into a set of numbers. Okay, these attributes that we're going to discover by using learning. Right, and the function is just of a certain type of learning class, hypothesis class, that's going to take these parameters, the input value, whether it's a training or test image, run some function, and then output scores. Okay, in this case, it's going to be a function that's going to output a vector of 10 numbers. Each number corresponds to some score about how good this particular image corresponds to one of those 10 classes. Okay, so pretty straightforward there, I think. So Actually, the classifier that we have for linear classification is extremely simple, right? We take the value of one of these numbers. Let's say the first pixel in the upper left-hand corner, its red value. That would be the first integer, right? And we call that, let's say, x1. So this vector x has 3,072 components. So maybe we take the first one, and we are going to associate a single weight, w1 here, to find the weight of how much that red pixel contributes to the overall classification for all 10 of the classes: airplanes, cats, dogs, etc. Okay? So you can see what we're trying to learn, right? We basically need weights here. This W matrix needs to be able to sum over, we need one for each of the 10 classes. So we have 10 classes as outputs. So we're going to get, this is what we're going to learn, is this model of 10 times 3,072 numbers, right? 30,000 parameters for this learning model. Okay, we also have a bias. We talked about this before in a linear classifier. If we don't have a bias term, everything has to go through the origin. Our vectors all have to pass through the origin. So if we want some offset, you can think of, the linear equation, yx times mx plus b, right? So the b is the bias. It allows the intercept to vary off of the origin. So we also can learn that. Okay, and so many times you'll see this b pushed back into the x vector. So we might have x1 through x 3072, and then we'll just add an x0 to help with the bias, and then we would have a weight for the bias. Okay. So how does it work? It's really simple, actually. So let's pretend we have this image here, right, on the left-hand side. Right? So we're going to play with an image that's only 4 pixels big. All right, and basically what we're going to do is think of a matrix multiplication, right? So these are the W's that we've learned. We're not going to say how we learned them yet. Okay, let's say we can learn them. And then all we're going to do is we're going to do matrix multiplication, which is just going to transform this set of numbers into a score, right? We're going to stretch the pixels here, this image x, into the form of a column vector, 56, 2, 31, 24, and 2, and just do matrix multiplication. We have our bias terms over here. This is our W0, okay, and this is W1. So this is the value for pixel 1, pixel 2, pixel 3, pixel 4, where 1, 2, 3, and 4 in that way, right? And we're going to multiply all those together, and we're going to get scores, right? So if you can verify it yourself, you could say 0.2 times 56, then plus negative 0.5 times 231, etc. Plus 1.1 will get us negative 96.8. Okay, so that's just a matrix multiplication, right? We have the W times X plus a B. Okay, so we get all these scores out, and basically we can think about this as then the scores are reflective of how likely that thing is to be the image. So in this case, it looks like the dog score came out highest, so we would have declared this a dog image, right? So that would have been wrong. Everything comfortable with that? So it's just a matter of taking an image, vectorizing it. So when we vectorize it, we get a single column vector. We multiply that against our coefficients that we've learned, which are weights, okay? And then we get a score out on the other side. Okay. So what is this thing actually doing? What is the linear classifier actually doing? Let's see. Well, we can go back and look at the weight matrix that it's learned. So this thing here, right, in the middle. And we can say, what does an average image look like that satisfies it when a cat score is high and the dog and the ship score is low, right? We can feed that back through. And then we'll get something like this, right? So we can unwind what a normal average picture looks like when its score is very high for plane and very low for everything else, right? Because we can work the linear algebra backwards, right? And we can fit what a normal X would look like that would maximize the plane value and minimize car, bird, cat, and other things, right? And then when we take that vector and then we reassemble it into an image, this is what we get, right? So it's not it's sort of intuitive, right? And a plane looks like it has blue mostly, probably sky, right? This car here looks like, you know, maybe there's a windshield at the top and some things like lights on the side. It looks fairly symmetrical. But there are some problems with using a single classifier, a single set of weights for this, because you can imagine, for example, look at this horse. Doesn't it look a little funny? It's got two heads. You're not going to ever see an image of a horse with two heads. Okay, but what is it doing? It's basically averaging over all of the input images. And usually when you see a picture of a horse, you know, they're orientated in one way or the other. The horse is either facing the left or it's facing the right, right? And because what we're doing with this very simple linear classifier is we're using one set of parameters, you know, these 30,000 parameters, but 3,072 parameters just for horse, it has no choice. It has to push everything into that representation. So we're getting a horse with two heads, right? Because that's on the average what it's going to look like, right? So there are definitely some shortcomings of this, right? So basically what's happening is for every one of those sets of coefficients, those W's associated with a single class, like 3,072 parameters, is dictating some hyperplane. So I'm just showing you this hyperplane in 2 dimensions, right? So it's going to draw a line or a hyperplane at the generality. And basically, depending on which way the norm is facing, we're going to say everything above that perpendicular plane classifies things that are of that sort. So this car classifier over here is saying that everything above this plane in the red direction is basically cars, okay? And when it's intersecting with the deer classifier, like over here, then we have problems. But when there's clearly one direction that's dominant, then we would say that is that type of object, okay? So that's how we would interpret the classifier. Okay, so you can see from the last slide, that's fine if you have data points that are nicely separated linearly, right? So all the things that you saw on the left side, most of them are cases that look pretty good. And you can argue that, you know, maybe if I draw this airplane classifier a little bit like this, maybe I would get better airplanes, but I also run into some boats here. But basically, maybe in this space, things are more or less linearly classified. Right? But if you go to other cases where your representation doesn't admit things smoothly falling into certain areas, then you're going to have a hard problem. So for example, for a linear classifier, we know it's a classic case that you can't represent an exclusive OR type of function, right? So the one on the left side where, you know, you have the number of pixels being 0, being odd, could be in this quadrant, and the number of pixels being even on these quadrants, then a single line won't be able to get you that, right? So we can't win here. We're out of luck. So we need to do something else. And what can we do? So we'll get to that in a while, but we can get an idea of what's going on from this by thinking about whether a W is good or bad. Right? So we want some way of assessing whether a particular W that we've been given, a model that we've been given, is good or not. Why do we want that? Because with an idea of the fitness of a model, we can then go back and say, well, if I have 2 models, which one I prefer? And then I basically have an optimization problem. I can prefer one model over the other and generate new models, and then I can test which ones are better of that. Right? So then we have some type of procedure for learning what are better models, right? Up until now, we haven't talked about learning anything. We've just been talking about evaluating, okay? So we need to be able to evaluate this function by giving a sense of whether W is good or bad. So for example here, for this cat value, this first column, right? I'm gonna look at all these W's, and we're going to say whether this column of values is good. So I've bolded here the correct class, or rather the Stanford people have bolded the value. So cat is the correct class. It gets 2.9. Automobile gets 6.4. frog gets minus 4.34. So you can tell from the first column, this is not the correct judgment because dog here gets 8.2. So this is an incorrect judgment from the classifier. And we would have rather had the cat score be a lot higher than 8.2 or the dog score be a bit lower and the deer score to be lower, right? So this is not a good case, right? So we're going to say here, W messed up. Okay, we didn't do a good job with that. For the second column, this looks pretty good. Out of all the numbers in this column, the automobile is the highest one. So that looks good for us. And for something like this tree frog, well, that was pretty unsuccessful, spectacularly unsuccessful because the right case is negative. It doesn't even think it's a frog at all. And the things that it thinks are positive are trucks and dogs, right? That's pretty bad. So ourselves, we can eyeball this and say, yeah, there are certain cases in which when we look at a particular test example, we can see whether the W's are in fact representing our output correctly or not. Okay, so we're going to do this for this lecture. This ends the first part of what we didn't finish last lecture, which is to say that what we want to do is come up with an idea of what a loss function is, right? To be able to quantify what it means to have a good W, right? Because with that, we start to admit the possibility that we can learn. Because we can look at two sets of parameters, two models, and say, I prefer that model over this one. And then we can do search, right? Because otherwise, we don't have that. Okay, and how do we do that search? Well, it means that we have to have some way of exploring the space and evaluating things using our evaluation function or our loss function. And that's going to be optimization, a separate topic, right? And that will get us to the last part of what we need to do before next week. Okay, all right. So that's this set of slides. So I'm going to go to this. I like PowerPoint better because I can draw. I can't seem to draw very well on PDF files. So now we're going to go over the lecture 3. This is the last lecture in the pre-flight, which is loss functions and optimization. So we talked about all of these in the last lecture. We talked about KNN, and we talked about setting the hyperparameters, which are like what number of K to use. And to do that, we would split the data that we have, all of this data over here, this whole set, and cut it into a test set, right? So we're going to hold that away from the classifier, train on the training set, and then assess whether the parameters that we get are W's if we're doing a linear classifier any good by testing on the test. But in order to do hyperparameter tuning, we can't do that because when we train on the data, we get hyperparameters that are sensitive to the training set, and we don't know whether they're any good to generalize. So we have to further split the training data into a sort of like training set and a training test set, which we call a validation. So we're going to train hyperparameter values over different parts, different values on the training set, test whether those hyperparameters are any good on the validation set, and then finally test the entire algorithm on the test set later on. For example, this curve that you saw earlier is a representation of how we do validation, right? We use the same training set, we set different parameters of K, and we graph their performance, and it looks like, okay, somewhere around here, that was a good value of K. So I'm going to use this K for the actual system that I'm going to build, and then maybe test it on the testing set, okay? We just talked about this, so I'm going to skip this slide. And basically what we're doing in this lecture is these two parts, defining what a loss function is and defining how to use this loss function to drive an optimization process. Okay, so we talked a look at this last time. We were basically saying, let's pretend we have a really tiny data set, with only 3 images and 3 classes. So again here, it's a version of what we saw last time. The same thing holds. Here we have a cat that was misclassified into a car that was correctly classified as a car, and a frog that was misclassified as a car. So everything is a car to this algorithm, right? Because all the maximum values are in the car row. Okay? So we want to understand what's going on with that. Okay, so we need to define a loss function, right? So given a data set of examples, right? So maybe we have n examples. So each example is, iteratively called I. So I goes from 1 to n, right? Where each thing, our vector input would be xi, meaning our data drawn into a long vector. And y would be the integer label telling us what class it is. So maybe integer 1 would be cat, integer 2 would be car, and integer 3 would be frog. Okay. Then what I want to compute is some type of loss function. Okay. I'm not going to tell you exactly what form this is yet, right? But basically, I'm saying that the loss function is like this. Okay. I have a function that I'm going to learn. This is the model, right? It's going to take the parameters w, like a linear classifier. It's going to take the input. Okay, it's going to predict the output given this function. So the output of this is a vector of numbers, right? And then we're going to assess whether it's correct against the actual label, right? And then I'm going to take all of this information, the output of, let's say, the free numbers for each class and the correct number, okay, with the correct classification, and compute this formula. I haven't shown you what this is. But basically a formula that says, how good was that, right? It's a loss function. That means lower is better. So if I get a loss of 0, that means pretty good. Everything is fine. Okay? If I get a positive loss, means I'm not doing so well. And all this is saying is that I'm going to sum over all of the elements in my data set. Any questions so far?
Sorry, so in this case, you are defining like label, let's say cat is 1 and class should be 2 and frog should be 3, right?
Yeah, I could say cat 1, frog 2, 3. So we're going to say yi is some integer label. So I can think of it as an enumerated set. Okay, so what this loss function is doing is taking free values, right? A value for cat, a value for car, and a value for frog, which is the output of my f, and then the correct label, whatever it is, some yi. Okay, these 4 pieces of information are going into our loss function. Then I have to compute what the loss is, right? So the hope is that if it was actually supposed to be a car, for example, in this case, right, then I would accord it a very low loss or no loss at all, right, because it got it correct. Right, but in the case of something like frog, where this number is very low and the algorithm actually thinks it's a car, then I'm going to say that was pretty badly misclassified. I think you can do better than that. Let's look for a set of parameters that can do better. Okay, yeah. Okay, so there are 2 loss functions that we're going to study today, which actually in machine learning they assume as prerequisites. Okay, but never mind, we're going to go over them. I think it's going to be pretty intuitive. One is the Multiclass SVM Loss. So without knowing what an SVM is, doesn't matter. What we're just thinking about here is what is the loss value. Okay, so the loss value for Multiclass SVM, it looks a little bit like this. So I'm looking at a training image, okay, that has the image here, xi, and a label yi, right? And I'm going to create a score vector right here. This vector is going to be free long, 1 coefficient for cat, 1 for car, 1 for frog. So you can see the output of that right here. This is the column vector that represents S for the first image. Okay, then the SVM loss has this form. Okay, so what's going on here is basically they've expanded this loss function into an if-then-else statement. So you can say here, there's one case and another case, and let's explain what that means. First, we're going to basically take all of the classes for which the answer, for which the label is not the correct answer. So let's take a look at this image here. This is a cat, right? We know cat is the correct label, but the classifier got it wrong. But in any case, since we know yi is cat, we're not going to evaluate the result over the cat itself. We're just going to evaluate it over car and frog. Okay? And what this is saying, for those 2 classes, car and frog, compute the following value, either 0 or this sum. Okay, it's 0 if the correct score, that means the CAT score, greatly outdoes the wrong class's score. Okay, so you can see this here. For example, I have a 4.9 here. Okay, the nearest class is frog, the farther class is cat, right? But both of these values of score are much less than car. They're at least one more less than the actual value for car. So in some sense, this top part of the loss function is just saying, am I really confident that I guessed correctly, right? Did I score the other classes low enough in comparison to the correct class? Okay? And if not, if I either misclassified it or my tolerance between what I wanted to get, the margin that I wanted to get between a good score and a bad score was too small. Maybe I correctly classified it as a car, but instead of writing 4.9, I wrote like 2.2. Okay, 2.2 is not far enough for a frog. It's not within my comfort margin, let's say. Okay, then I'm still going to give it a loss. I say, I think you can do better. You can try to find a model that pushes these two things far away from each other. Okay? And if I take this loss function and I do away with this if then else case statement, I can write it like this, a max function. Just take the max of these two values. Okay, because that would be how it works. Okay, so you can study this. This is basically the condition rewritten into this form and then plugged into the max function so that we get one thing overall. Okay, so what this means is for all classes that are not the correct class, okay, go through and compute the loss for each of those other classes. So if I'm looking at a cat image, like this one here, I'm going to go look at the car case and the frog case and then see which one got a good score, right? If I got a good score, I would have a loss of 0 because that would be the maximum. If I got a bad score, then I would have something else that gives a positive loss and I would have incurred some value as a penalty. Right here again, let's make it clear. We're doing loss, okay, which means positive values are bad. So here, when we take the max, we'll either get a 0 or we're going to get some positive value.
So +1 is like not necessarily +1, so right? So maybe we can use +2 or +3 or.
Yeah, you can use whatever you want. You could use 4, 5, and 6. Here we're just saying that you just have to iterate over all of the classes. So maybe a natural order would be 0, 1, 2 if you're comp sci. If you're not from comp sci, you may pick 1, 2, and 3 or whatever. Okay, good question. Any questions so far?
I
think it's epsilon.
Which one are you talking about? This one here?
Yeah.
Or you're talking about this one? Well, is that right? Okay, so the one actually doesn't make a difference because of the way SVM works, which we're not going to get into. It's a scaling value. So no matter whether you fit a 1 or a 10 or a 4, what happens is your W's, the model for your SVM changes, and it will scale up or scale down. So actually, whatever number you fit here doesn't really matter. Okay. So when we view this as a graph, you may hear the term hinge loss. So when you think of a hinge, you can think of a door hinge. That's what it comes to look like. You know, if you see architectural diagrams, it'll look like that. A hinge where a door opens. So what we're graphing here is the score of the correct class and the score of another class, right? And basically what we're saying is that when the score of the correct class, which is on this axis, okay, greatly exceeds that of the opposing class, the wrong class, okay? Let's say, for example, here, all right? Let's say over here, okay? This means I have a very high score for SYI because this is the x-axis, maybe something like 4.9. And I have a very low score because the y dimension is low for SJ, maybe like 0.1. Okay, in this case, I'm pretty confident in this part of the landscape over here that the correct class is actually correct. Okay, and if I'm over somewhere like here, right, that would be the opposite, which I'm pretty confident that one of the incorrect classes is the right one. Okay, so what we want to do is graph this hinge loss. Okay, basically, as soon as I pass this margin, it means I'm getting the answer correct because I have more belief that the correct class is correct than the incorrect class. Okay, but I want it with some margin of tolerance. So when the scores are very close to each other, I'm still going to penalize and say, you know, you're getting the right answer, but you're not very confident. Okay, so I'm still going to apply some positive penalty. Okay, so basically what this is saying is at this point, when the distance is more than 1 between the previous, the incorrect class and the positive class, right, I give it a 0 loss. Means you're confident enough and you have the right judgment, I'm not going to penalize you. Okay, but when I have something where the difference is close or it's incorrectly classified, then I'm going to give you a loss, and that loss is linear, so it will go a straight line in the diagonal direction. So the more confident you are in a negative class, I'm just going to penalize you a bit more for that. Okay, so that's how we understand this graphically when we plot it. We're basically plotting Sj against Sy and saying when the margin is less than 1, then I'm going to give you some penalty. Okay, so that's basically the abbreviated form of the multi-class SVM loss. It means we just cycle through all of the 10 classes or all 3 classes, not doing the one where it's the correct class, just looking at all the incorrect cases and seeing whether the prediction favors the correct class or not. Okay, so we can compute this. Let's do this one time, right? So for this one here, right, we're going to take the first form, okay, which is, okay, because we skipped the cat because cat is the correct case, so we're not going to deal with that. So we're going to take the car. We're going to take the max of 0, and then Sj, which was 5.1, minus Syi, which was the correct class, which is this number here, 3.2. We're going to put that together, plus 1. Okay, that's the first part of this formula, right? And then for the second incorrect class, frog, I'm going to take the max of 0 and this number here, minus 1.7 minus 3.2 plus 1, which is a negative value, right? So then there's no problem there. Okay, so this will end up being a 0. The second term will be a 0. The first term is obviously a positive value. That's 2.9. So for this particular image, just this one here, right, our loss using an SVM multi-class loss is 2.9. So that's some figure of the badness of how well this classifier is doing on this particular image. Okay, and then we're just going to sum this type of SVM loss over all of the images in our data set. So we did it for cat, then we'll do it for car, then we'll do it for this. Questions so far? And there are going to be a couple questions that the lecture has for all of us, so we can try to work that out. Okay. So for the car one, you know, intuitively we think this is okay because the car class came out on top, and you can see how it's working, right? You're basically getting 2 0 terms because the margin between the car and the other 2 predictions is pretty big, right? It's pretty confident that that looks like a car, okay? And for the final one, well, we already knew this was not very good to start with because the correct class is negative. Both of the other ones are positive. So here we get the max between 0 and 6.3 and the max between 0 and 6.6. So that's a pretty bad loss of 12.9. Okay, so our overall loss would be 2.9 plus 0 plus 12.9 divided by the number of images, 3. Okay.
Once you are confident that the weights are correct for a particular class, we don't actually re-examine that class again under this mechanism.
Yes, for that particular image. And this is a very particular thing about multi-SVM class. So if you've learned anything about SVM before, you will know it tries very hard to get an image correct and cross the threshold. But after it crosses the threshold, it doesn't care about it anymore. So we're going to elaborate on what that means as we go through logistic regression loss as well as the multi-class SVM loss. So that's a good point. Any other questions? No? Okay. So let's say, for example, the lecturer asks, what happens to the loss if the CAR scores change a little bit, right? So let's go back to these CAR scores and permute them a little bit. What will happen? Let's say we move this down to 5.0, this one to 4.8, and this down to 2.4, right? What's going to happen to our loss?
It doesn't change a lot.
It doesn't change a lot, right? It won't change a lot, but in particular, it doesn't change at all for the things that it already got correct, right? And because this is a linear formula, even though you got it terribly wrong or not, it's not going to reduce a lot. So you're exactly right. You know, this 12.9 is just going to go to 12.7, right? Because this coefficient is being used twice, right? Once when you're comparing for cat and once when you're comparing for, in this case, it'll just be used once because it's comparing against frog. So it'll be 12.8. My apologies for that. Okay, so we vary CAR a little bit, right? These scores here, not much is going to happen. And we also can ask ourselves, and this is really good for when you are trying to code these algorithms. So you have some invariant properties that you need to understand. So when you program it, you can check the sanity of your algorithm. Because otherwise what you do is you code an algorithm, you get some results, you have no idea whether it's right or not. And you just sort of like give some intuition that if it works well on your data set, it's working correctly, which is totally not the right thing to do, right? You have to provably know that your algorithm is correct. So what is the minimum and maximum loss possible for a set of images? If I give you a set of 10 images, what's the minimum or maximum loss? Let's start with the easy case. What's the minimum loss?
0.
It could be 0, right? If I get everything right and I get it right by a large margin, right? All of the incorrect scores are much smaller than the correct scores, then all of them will be correctly classified, then it's 0. What's the maximum score? Yeah, positive infinity. Even for one image, it's possible that I really, really confidently, or I score it very, very high for the incorrect class, right? So there's no bound to the maximum loss that this system has. Okay, and that's going to cause problems because when we have infinite, it's hard to interpret what that means from a score possibility. So that's going to motivate us to move to a regression where these scores have a meaning. Right? We want the scores to have meaning, so we're going to make them into probabilities. Okay, so that will come up later. Okay, so for example, if you go code multi-class SVM on your own, which you certainly can do, it takes a while, but you can do it. All right, and you get a loss that's, you know, -5, right? That just doesn't work, right? Because the minimum loss that you can have is always 0 in this case, okay? So these are some invariants that you want to understand about the algorithms. So when you work on an algorithm or use an algorithm, you know its properties, you can sanity check your results, right? Because if you're just a data analyst, you don't know any better about the algorithms, you run the algorithms, they give you complete nonsensical result to a machine learning person, but as a data analyst, you may not know any better, then you're just going to trust that the data is correct and not be able to understand why it's not working. At initialization, W is small, so S is all 0. So what is the loss in this case, right? Let's say we set our W's all to 0. Okay. So then what's going to happen to our scores, right? How do we understand when we set our W's very small that the S's will all be 0? Can you guys understand this statement? Can you speak up a little bit? Right. Okay, can we understand that? So if we have all these W's here, right? And let's say that all of the W matrix is close to 0. When we multiply 0 times an X, they're all going to be mostly very close to 0, right? So that means the score for this vector, right, that comes out of this process where we're just multiplying the matrix W, which is our weight vector, you know, doing a matrix multiplication against the column vector X, is just going to get us a lot of small values. We sum all those small values together, we still get a small value. Okay, so basically what this is saying, if we don't initialize randomly, but we just set everything to 0 first, okay, and we want to learn from there, say start with a baseline, okay, then all our scores are going to be 0. What do you think the loss is going to be? Going to 0? Everyone agree with that? It's going to be 1.
The number of class.
It's going to be the number of classes. So let's say we have C number of classes like 3, right? Then why would we get 3 out as a loss function, the loss? Do you guys all get this? Because what's going to happen is all these scores are going to disappear, right? They're all going to be 0, right? Because we already just said all these outputs in this vector will be 0. So let's imagine I have 0, 0, 0, and 0, right? And then I'm going through this formula for all C minus 1 incorrect classes, right? And I'm going to compute the loss score, right? Well, the loss is 0 minus 0 plus 1, right? So what's that going to give us? Plus 1 for each of the incorrect classes. So I have 2 incorrect classes here, so I get a 2, right? So I'm going to get 2, right? It's going to basically be the number of classes minus 1. Does everyone see that? Because basically all of this entire score vector for every image is going to be very small because we're going to initialize with a 0 weight, right? All of our W, our coefficients in our weight matrix is going to be 0. Okay? So again, this is a checking property that you have when you run a multi-class SVM. Okay? Initialize all your weight vectors to your model parameters to 0. Compute the loss. If you're getting something that's way off from the number of classes minus 1, that means something is haywire with your algorithm. Okay? Again, this is some form of proof checking that we use just to make sure that your algorithm is actually coded correctly. Okay? So don't fall into the trap as a machine learning person to validate yourself by saying, oh, I got good results, therefore it must be working properly. Okay, it doesn't work like that, right? It's either mathematically correct or mathematically incorrect, and there's no two ways about it. Okay, so you just have to make sure your results are correct, and you do that by using toy examples. You do that by knowing some invariants about the properties of your machine learning. Okay, what if the sum was over all classes, including j equals yi, right? So we purposely decided not to sum over the class where I include the correct one. So what happens then? Right, so if I have the correct one, then this sj would be syi. So syi minus itself would be syi, right? So this term would just go to 0. And I'd just be getting an extra plus 1, right? So actually, there's no particular reason why we excluded this. It's just, maybe logically it makes sense to not think about comparing the correct class against itself. But even if we do, and sometimes we might do it anyways, okay, the values that we have in our loss are just going to be 1 off from the correct one. But also, if we think logically about a loss, right, we would want to say if you get everything correct, your loss should be 0, right? So it wouldn't make sense to compute it over the correct class and have a minimum loss be 1, right? Because in some sense, it doesn't have a very nice semantic interpretation. Okay, this is why we exclude the correct class from the multi-class SVM hinge loss. Okay? All right. So what if we took the mean instead of the sum? If we averaged out all of these,
So it's just losses divided by the number of classes, right?
If you have more and more classes,
if you have more and more classes,
then the value of your incorrect things go down.
okay, so maybe we're going to lose a little bit of resolution if we use a mean instead of a sum. Can I interpret your answer like that? Do you guys agree? I didn't work this one out yet, so you guys can tell me what the answer is.
I mean, it can be better or worse. It depends on the distribution of the losses.
Okay. Right. So we use a mean. I mean, we replace this with an average, right, rather than a sum.
I think if there's a lot of correct classifications, then since you're excluding the correct ones from your mean, that's going to affect things because you're only taking the mean of the incorrect ones.
Yeah.
So say you only have one mistake, and that gives you a loss X. But if you have two mistakes with each individually less losses, you'll have less of a loss because you've taken which may not.
Do you guys agree with that?
Actually, I don't think that will make much of a difference as long as it's like you set a correct learning rate for your loss function and proper like step size. Because like mean and sum, they basically represent the same thing except that it's just divided by constant, which is the number of examples and observations.
Okay. In fact, we often, as we saw before, we sum all of these losses together anyways and divide through by the number of examples. So we're doing some type of average already, right? So yeah, I don't think it makes that much of a difference, right? We can just logically think of it. It's easier to compute a sum. Okay. Yeah, because we would have to loop over all of the examples. Yeah, and when we get to efficiency, that's going to be a very big thing because anything that requires looping over all the training instances requires a lot of work, right? Especially if you have a large data set. And that's going to motivate some type of batching algorithm that we'll see in a short while, right? Okay, what if we use something like this, a squared loss instead? Okay, so the only difference here is we have this extra thing here. Sorry?
Right?
It's better? Why is it better?
Exaggerates, so there are small differences. Squaring, it makes it bigger. Squaring of this bigger, right? More sensitive to.
It'll make things greater than one bigger. It'll make things smaller than one smaller,
Yeah.
right?
So you will make things that are very similar. So let's say you got the score is very similar to the actual date each other. You will make the loss for that smaller. So now it becomes harder to distinguish in your result.
What we can think about, and you're going to see this over and over again, is that when we move to exponential loss like this, a squared loss usually, is that it exaggerates the difference between scores. So if we go back and look at this hinge loss function, which we saw here, it'll look something like this instead. We'll say, okay, it's still got 0, this component here. Okay, but as soon as we get otherwise, we're going to have this squared loss. I can't draw a 2. I'll try again. Okay, and that means it'll go something like this. Okay, so it means that when we have things that are really off, like this one is really bad, it's very far. It's about 6 far away. That's going to be penalized at a rate like 36, right? Whereas instead something like this, which is wrong but not terribly off, right? This is off by 2, then it's going to be just a 4. So 4 compared to 36, that's a big difference. But 2 compared to 6, it's not that bad, right? So in multi-class SVM, when we use a linear loss, that's exactly what it implies. It's just a straight line. So bad things are linearly bad, right? But we all know that some mistakes are really bad, like you drive your father's car into the wall. Okay, that's really bad. You're going to be grounded for life. So that's a really bad mistake. So yeah, maybe having an exponential loss makes sense for certain types of very egregious mistakes. Okay, so why do we ask this question? I think it's because we want to motivate another type of loss function that we're going to get to. So in any case, let's look at how this is computed. If you were to write this out in code, actually when you use NumPy and Python, it's very compact. Okay, so we can just do something like this, right? Have a loss function that takes in an example, and here's the model. This is our parameter. So when we have a parameterized model, that's what we mean. It's just a set of coefficients that compactly represent the hypothesis, right? So I'm going to do the dot product between the scores and the model. Between the model and the input, and come up with a bunch of scores. This is a vector. This is our S vector for all the free or 10 classes, right? And then I'm just going to compute this formula. This is our L1 loss, right? This says just take the max of 0 and the score and the score of the correct class plus 1, right? And then I'm going to zero out the margin for the correct class, because otherwise it would be 1. Okay, and then just sum them together and return that. So this is the entire loss function in 4 lines. Okay, but it's exactly corresponding to what you would do. Okay. So suppose we found a W such that the loss equals 0. Okay, that means it gets everything correct on what you gave it. So I gave it a set of 10 images. It got all of them correct by a comfortable margin. Is this set of model parameters unique? No, because there could be a lot of parameters, W, that do this. In fact, we saw this in the car example. We saw when we perturbed the car example a little bit, only the ones that it incorrectly classified as a car get disturbed, right? The case where we had an example where it correctly classified car, you know, even though we changed the W such in a way that the score for a car changed, it didn't affect the loss value, because the loss value was still comfortably above the margin of error for classifying it as a car. Okay, so what SVM loss is doing, as I sort of hinted earlier, is that it's working hard to push all of the examples to be correct. That's why, you know, we're optimizing to a loss of 0, right? But after that particular image, you know, let's say the cat gets correctly classified to cat instead of car, and it does it with a comfortable margin, the algorithm doesn't care about it anymore, right? Because the loss is 0. There's nothing to optimize after the loss is 0, right? So the algorithm is going to turn its attention to only the things that are continually misclassified. So as soon as it gets an example correct, fine, I don't care about it anymore, right? Okay, so in fact, as we talked about earlier, we were talking about whether that +1 could be a different value. In fact, it can be. It could be any value. In fact, there's an infinite number of values where you can change the W by a scaling factor, and you would still get the same results depending on the coefficient that you put there. So we just arbitrarily set it to 1 so that we don't have to worry about it. Okay? So really, what SVM is trying to do is tell you that there are an infinite number of hyperplanes that can classify it if it could be classified correctly by a set of hyperplanes. Okay, and you can see this here, right? If I take a W that's twice as large, it's just going to spit out values that are twice as big. So you see this 3.1 comes to 2.6. This 2.0 comes to 4.0, right? And so with W twice as large, when we get a loss of 0, it's still going to be 0. So all of these cases, 3W, 4W, 5W, on the case where the data set is in fact linearly separable by W, all of the other coefficients of W will do just fine. Okay, because that's the property of the linear form, right? Up to a certain scaling parameter. Okay, any question about that? Nope. Okay. So basically what we were saying here is that we're going to compute this loss function. We gave you one version of it, the SVM multiclass loss, right? We're going to throw it into this equation where we're going to evaluate it all over all of the images in our test set and then divide through by the total number of images, right? And that's going to be our average loss, which we're going to deem for the loss set of this particular set of model parameters W. Okay, and we can think of it like this. Okay, I have some training data and I have to fit some parameters W. You can think of these as coefficients to the x's. So if I think of a particular data set which only has one attribute, let's say x1, okay, and x2, and I plot these data points, okay, and I want to fit a line through it, then I could draw a line like this that would exactly classify that would hit all of these data points, right? Basically, this is some type of high order polynomial that can do that. Okay, but we wouldn't say that this is very good because although we're getting all of these dots correctly predicted, the values of them, okay, we won't think this looks like the general case of what's going on, right? So we can get a model, a W, that represents a 0 loss. So this is a 0 loss case because the blue line exactly goes through all of the examples that we want. Okay? But it might not generalize. So if I get new data in, also drawn from the same distribution, maybe it looks like these squares, right? And so what happens here is even though when we train the system, we got a loss of 0, in some ways, sometimes we can make the function behave in such a way to exactly fit the data that we've given it as training. But it won't generalize because it's too complex for the type of phenomenon we're trying to capture. Okay, this is something that you may have heard before. It's called overfitting. Okay, so what does that mean? It means that the model that we learned is somehow not generalizing, but trying to fit the data and capture it exactly as is so that we can get a loss of 0. Because our optimization is supposed to be giving us a good value of loss, right? That we want the loss to go to 0. So this curve does that. It hits all the data points, so it gets a loss of 0. But that's not what we want. We want a loss of 0, but somehow the way we're capturing it being just high fidelity to the data is not enough. So we might think this line looks a lot better. Why is that? Because it looks like it fits the blue dots very well, but somehow it's not as complex, right? It doesn't try to fit everything exactly. And because it doesn't try to fit everything exactly, maybe it will generalize better. Okay, so in this way, we are going to say maybe, you know, when you have your coefficients or your W's, you want to make them in such a way that they can generalize. So you can see, for example, this blue line represents some higher order polynomial, maybe something with x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, with different coefficients W1 through 5, right? But this green line that I've drawn, it's really simple. It only has a W1 and an intercept, a W0. I only need 2 coefficients to tell you what that is. And because this model is very restricted, it can only draw straight lines instead of these high-dimensional polynomial splines. It's in some ways simpler and should generalize better when given new data. Okay, so that comes to another part of machine learning, which you'll hear a lot of too. When you hear about overfitting, the next word you'll hear is regularization. Okay, so regularization is just saying that when I create a model, okay, and I want to optimize that model, I want my model not to overfit, not to fit beyond what I think is the general trend. Okay, so when I capture data that I want to machine learn over, okay, oftentimes we can think of most of the data has some signal, but there's some things that I captured and it's noisy. For example, I have a sensing device, an X-ray machine. It, you know, sometimes got dust in it or whatever, so some of the pixel values are not completely accurate. Okay, or there's some obstruction or some, you know, I don't know, microwave energy, or somebody's using a cell phone at the same time, interfering. Okay, so your sensors are not usually perfect. They don't capture exactly the data that you want in. So there's going to be noise in your data. Okay, now a machine learning algorithm has no way of knowing whether things are noise or whether it's signal. It just sees the data. So it's going to fit the data as best as it can. Okay, so when you give it the blue dots in this picture and you don't have the regularization term, okay, it will try its best to optimize LW to be 0. Okay, it doesn't matter, right? Because you want to optimize that. So we use regularization as sort of a penalty, another loss, okay, to say that when you choose W's that are like really big, okay, then I'm going to penalize you. Okay, so for example, this wavy line here, it's got coefficients of x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, x to the 0. Okay, so all of those are different parameters. And to fit this crazy line, maybe the x to the 5th power is like very big, like 27 or something like that. Okay, something big. Okay, but this line here, it's got all of those other powers except x to the 1st and x to the 0 set to 0. Okay, so in some sense, regularization is just saying, I want my model to be simple. I want you to pick small parameters in your model. So my W coefficient shouldn't be large. I shouldn't have an x to the 5th that has a coefficient of 27, because that just helps me fit right through there. If I had 25, maybe it would fit right over here. If I had, 5, it would fit over here. So to make it exactly go through that point to get a loss of 0, I'm going to pick some absurdly high parameter value for W. Okay? Okay, if you don't quite understand it, just think of it this way. Regularization is forcing, or encouraging, I should say, through math, right, us to pick models that are simpler, okay, that don't necessarily fit the data perfectly, but trade off fitting the data for having a simpler model. Okay, so this is what we think of as a realization of Occam's razor, right? So if you have two different hypotheses, they explain the data or the signal equally, wouldn't you go with the more simple hypothesis, right? Because that's more likely to generalize, because you're making less assumptions. Okay, so that's where we're going with this. Regularization is that. Okay, so to sum up this part of the lecture, basically we have something that will look like this. All right, we have this function here, which we just described. This is the whole loss function. Okay, and then we're going to add this regularization parameter that we'll look at later. Okay, and this regularization parameter takes various forms. Okay, you'll see this one a lot, which is what they call weight decay or quadratic loss function. So basically, we take the weights W, and then we square their value, and then we use that as a penalty. So if you set a coefficient, any of the coefficients very large, like 7, 8, 9, 10, then you square that, that becomes 49, whatever, 64, 81, 100, then it's going to create a very big loss. Okay, you can also use L1 regularization, which is what we looked at earlier, which is just, just take the scores of all of the coefficients and then add them together. Okay, so if I have W1 through W5, I just add up all those coefficients, sum them together, and that will be my regularization. You can also have both of them together with some trade-off value, which is beta. Okay, this is quite common in recent decades or so, and other things like that. Okay, you'll see dropout later when we go to neural network training. Okay, but Basically, all of these different ways that they've illustrated on this slide are ways just to try to enforce that the model is simple, with the hope that with a simpler model, it will generalize better on unseen data. Okay, that's all. Okay, so let's take a look at this for a sample so that we can understand where we're going with the idea of regularization, and it will motivate the second part of the lecture. All right, let's pretend we have some x values, right? So I have 4 pixels, they all have the value 1. Okay, and then I have a weight vector here where the first component is 1, the rest of them are 0, and a W2 which has the same sum, okay, 0.25, 0.25, 0.25, 0.25, okay, and I want to look at how the weights are going to differ. Okay, so if I look at an L1 version of this, right, let's say I use L1 regularization, which just says sum up all of the coefficients, and that's your loss, your regularization loss. Okay, well, 1 plus 0 plus 0 plus 0 equals 1, right? And 0.25 times 4, because I'm adding it 4 times, is equal to 1. So our L1 loss for both of these weight vectors is the same, 1. But if I do L2 loss, which one is bigger? W1 is bigger, right? Because I have W1, this is going to be squared, 0 squared, 0 squared, 0 squared. So I still get the same L2 loss, which is 1. But when I square 0.25, it's going to shrink a lot. For very small coefficients, W2 looks better, okay? It thinks that this weight vector is better, okay? So, okay, we're not going to get into this. If you know Bayesian statistics, then you would think it corresponds to what you would learn in ridge regression. Okay, if you come from a stats background, okay, it corresponds to maximum a posteriori inference on using a Gaussian normal prior as noise. I mean, we go over this in our machine learning class, but not here. Okay, so why is this important? Okay, I'm going to show you the old slides that we had earlier, and I'm going to try to bring that together. Oh, this is lecture 2, yeah. Can I go back or not? Okay, this is the one I wanted to show you. So L1 and L2 are related quite a bit. So when we think of L1, okay, and don't think of it in terms of these pixel values for a second, okay? Just think of these two as 2 different coefficients. I have my W1 on this axis, okay, and my W2 on this axis, okay? And let's say my regularization value is 1, okay? That means, for example, in the case here, I could have set, let's get rid of these 2 here, okay? These 2 things here, okay? Then basically, if I have a budget of 1 in my regularization loss, I have to either put it all here, or find a way to linearly move it between these 2 numbers, right? For example, to get a loss of 1 in this regularization, I could have set it to 0.5, 0.5. Okay? So in some sense, it looks like this diamond here. You can say I can set W1 to 1 and W2 to 0, or I could set W2 to 1, W1 to 0. But if I want any trade-off, there's a linear trade-off, right? That's what this diamond shape represents. Okay, when we go to W2, because we have this squared loss here, this corresponds to Euclidean distance, right? So if I, for example, have 1 and 0 here, I will still get the same loss value as that, right? So that corresponds to sitting over here. Okay, but for example, if I just change this a little bit, like to 0.9, okay, 0.9, then I can take a big step in this direction, right? Because I've gotten 0.9, that's 0.81, so I have 0.19 left over for this coefficient, right? And then that coefficient can be pretty large already, in order to get 0.19, right? So that corresponds to basically, I really hate large numbers in L2, okay? I want to make all of the parameters in my W small, okay? I don't accept any one coefficient to be big. This is why if I have a large value of, let's say, W1, by trading off a small value of that, I already can accept a lot more budget in the other zeros to be non-zero, okay? So why does this matter? Because in L2 loss and L1 loss, we're making different assumptions about what is important. Okay, L2 loss, this one here, L2 regularization, is basically saying that I want all of the coefficients to be as small as possible. Okay, but I don't want to force any of them necessarily to be zero. Okay, because I want to spread the influence of all of the weights through all of the parameters. So in sense, what that means is that if you're thinking about it from a vision perspective, every pixel has some importance. Because every pixel is getting some weight. None of the weights are necessarily going to be zero, because if I have a zero, that zero could be slightly larger and trade off a bigger downward trend from another coefficient. Okay? If I have L1 loss, right, this is saying that, you know, the total sum matters. Individual pixels might not. So for example, in this case here, this loss is perfectly fine. It's equivalent to this loss in L1. There's no difference. But this loss is saying something, this weight vector is saying something very specific. It's saying that the other 3 pixels don't matter at all to this problem. You know, the only thing that matters to classify this image is the first pixel, right? Whatever data you have in the other ones, I don't care, okay? So that's what L1 and L2 are doing. L2 is somehow much more holistic. It's saying everything matters in small proportions. Everything is not evenly spread apart. So that's why last time I told you that, you know, L2 is usually used for the case where you have like objects, right? For example, in images, everything is a pixel. Okay, there's not one value in the vector that represents age and another value that represents gender and another value that represents income levels, like you would have in other applications where you have your vector representing lots of different discrete types of information. For that, L2 probably doesn't make a lot of sense. Okay, so now we're going to learn the second classifier. But I think we can take a break for a little while if that's all right with you, because I'm getting a little thirsty. So we'll stop for 5 minutes, and we'll talk about the second half on softmax. Okay.
So,
Mm-hmm.
yeah, Professor.
Yeah.
So I'm actually an undergraduate from the concept, but yeah.
Okay.
For this lecture.
Sure.
And so